In this video, we'll study about the SR flip-flop. SR flip-flop is nothing but set reset flip-flop. So, in this video, we'll study about the circuit diagram of each flip-flop. Then we'll study about the truth table. Then we'll study about the extended truth table. That is nothing but the characteristic table. The characteristic table is actually used to find the characteristic equation of flip-flops. After finding the characteristic table, we'll go for excitation table. And these excitation table actually help to convert one flip-flop to another flip-flop. In SR latch video, we have studied about the circuit diagram of SR latch. So the SR latch actually made up of NAND gate or NOR gate. So let us consider SR latch using NOR gate. So the circuit diagram is looking like this. So we have one NOR gate. Again, I have another NOR gate. Okay. So these are the output. Let's name it as Qn, and this is Qn complement, and each one input of flip-flop, each one input of the gate will be equal to the output of another gate. Similarly here, we like this. Okay, and after we have studied up to this. Okay, so we say that these two lines are actually S and R, and here we have Qn and Qn complement. This is nothing but the latch. Okay, and now we are studying the flip-flop. Flip-flop is the clogged latch. That means if we have taken another AND gate here, okay, so two AND gate, I'll take two AND gate, and we'll give two input here, that is S, and one more is R here, okay, and we combine this together to give the clock pulses, okay, CLK. Sometimes written as CLK or CK or CL or CP clock pulse. This is a AND gate. Truth table of AND gate says that if both the input of AND gate becomes 1, then output becomes 1. So let's name it as gate 1, gate 2, gate 3 and gate 4. Okay, so I know that the truth table of AND gate, when both are high, input 1 and 1 gives rise 1. Okay, else that means what else the input will be, output will be 0. Only one condition exists. Yes or no? Yes. So this is the truth table of AND gate, and we also studied the truth table of SR latch, that is S, R, then Q. So we have studied like 0, 0, 0, 1, 1, 0 and 1, 1. Okay, when 0, 0 corresponding this, we have seen that it is hold state. That means Q. Q means hold. Then here we have 0, that is reset. Here we have 1, that is set. And here we have invalid condition. Okay. So now this total circuit is the combination of inverter and latch, inverter plus latch. So this much will give the work of inverter and this much will give the work of latch. So this circuit actually called SR flip-flop. And to develop the truth table of SR flip-flop, we should know that the truth table of AND gate and truth table of SR latch. Okay, you go for clock, then S, then R, then Qn, then state. We'll find out what happening, right? So you can see when my clock is 0, clock is like this, na? When clock is 0, I told you when input of AND gate both are go to high, then we have a chance to go high in the output. But if anyhow the clock is 0, output must remain 0. Clear? and this is the internal circuit. That means when clock is 0, I do not know what are the output of this place. Clear? So you can see if my clock is 0, irrespective of the SR value, my Qn is equal to Qn. That means hold state. Clear? Okay. I'll put my clock to 1. When my clock goes to 1, if I make S is equal to 0 and R is equal to 0. Clear? If my clock is 1, I'll make S is equal to 0 and R is equal to 0. So what is the output here? Obviously any one input 0 means output is 0. So here we'll get 0 and 0. Okay. So in the latch truth table we see when there is 2 0 in input, Qn will be Qn. This is a hold state. It's called Qn. This is also hold state. Then after we'll make S to 0 and R to 1 and my clock is always 1 now. See, when I make S to 0, R to 1. So here S is 0, R is 1. In gate 1, any one input is 0, so output must 0. Okay. But in R, I told you clock is high, clock is 1 and I make R is equal to 1 here. So 1 and 1 gives rise output here to 1. So input to the latch is now 0 and 1 and from the truth table 0 and 1 corresponds to 0. So we have reset here. Now I'll make S to 1 and R to 0. Here I also make clock as 1. Okay. Now clock is high, S is high and R is low. Any one input of AND gate low means output low and output is 0 here. And for this S is high, clock is high, so output is high. Okay. So now the latch input will be 1 0 and corresponding to the truth table 1 0 represent 1, that is here you can say it is set. Okay. And now if I make both S and R to 1, so S is 1, R is 1 and clock is high, so both the inputs are high, so output will go to high. Here output also go to high. So now 1 and 1 are the input of this latch. So 1 and 1 gives rise, 1 and 1 with high clock gives rise invalid condition. Okay. So from this we have designed this. Okay. From this table we'll see that when my clock is 0, we should not consider the SR value. But as we have to consider the SR value, then I have to give the clock pulses. So irrespective of all those things, this much is my truth table for SR flip-flop. That means to operate the SR flip-flop, I have to make my clock pulse high. So the table now reduced like this. This is my S, this is my R, this is my Q or Qn. This is state. This is called truth table of SR flip-flop. Clear? So once we find the truth table of SR flip-flop, we have studied about the truth table and we need to study about the characteristics table, and the characteristic table is nothing but the extended version of the truth table. Okay, so it's called characteristic table. Characteristic table take the input S and R and it make a relation between the previous state and the next state. So let's study about this. So S and R, let us consider this is Qn. Qn is the first state. What is the next state? The next state will be Qn plus 1. Clear? That means characteristic table create a relation between input, present state and the next state. Okay. So these two are input. This is my present state and this will be my next state. Clear? Okay. So for each value, let's take S as 0, R as 0. So S0 R0. And for S0 R0, Qn is Qn. But do I know what is Qn? Qn may be 0 or may be 1. Clear? That means we have two combinations. For 0 and 0, we may get a 0, we may have 0 in Qn or may have 1 in Qn. But after clock, what happened? Qn remain Qn, means whole state. That means whatever the state, the next state will be the same as the previous state. So we'll get 0 here and 1 here. Clear? So this is corresponding to SR as 0 and 0. Okay. So when you go for S is equal to 0 and R is equal to 1, what happened? So I do not know what is the previous state. Previous it may be in previous state. Previous state may be 0, may be 1. Clear? So for 0, 1, previous state may be 0, may be 1, like this. So without bothering the previous state, if my you can see from the truth table, without bothering the previous state, if my S is 0 and R is 1, the next state must be 0. That means without bothering 0 and 1 and without bothering the previous state, the next state should be 0, 0. Clear? Okay. Let us study about 1 and 0 combination. 1, 0. Similarly, we have two combinations, na? 1, 0. So because I do not know what is my previous state may be 0 or may be 1. I do not know. So for 1, 0 combination of SR, from truth table you can see 1, 0 combination, without bothering the previous state, the next state should go to high, 1. So I do not know what are my the previous state. So without bothering the previous state, my output must go to high. Clear? Likewise, for another combination as 1 and 1 combination, 1, 1, I do not know previous state 0, 0. Okay, 0, 0 or 1. I have no idea, na? 0 and 1. And for any combination of previous state, if my S and R are 1 and 1, so the next state will be invalid state. I should not bother about this. So this table, from this truth table, we extended it to get characteristic table. Okay. So this is the characteristic table. If you take these are three variable, S one variable, R is another variable, Q is another variable, we can say 0, 0, 0, 0, 0, 1, 0, 1, 0. It's like decimal 0, decimal 1, 2, 3, 4, 5, 6, 7. Okay. If you try to design the K-map, we have get a K-map of three variable. Here it is S complement, here is S, and remaining two variable R and Qn, we can write R complement, Qn complement, R complement, Qn, R Qn, and here R Qn complement. 0, 1, 2, 3, 4, 5, 6, 7. And from this characteristic table, if you take Qn plus 1 where is high, so Qn plus 1 is high here, here and here. So 1, 4, 5, you can write 1, 4, 5. And we have to take the don't care condition, these two as 6 and 7. And if you 6 and 7 are don't care, if you make a quad, it will come like this. Okay. And if you make a pair, it will come like this. So for Qn plus 1, we have the equation as, so in this row, S is not changing. So we'll write S plus, in this column, Q complement, R complement, Qn is not changing. So R complement Qn. So that means from this equation, so this is the characteristic equation of SR flip-flop. After studying the characteristic table, we will study the excitation table. If my Q is here, Qn, and Qn plus 1 is here. So this is my previous state and this is my next state. And okay, so I have two combination, that means 0 0 0 1, and for previous state 1 0 and 1 1. So 2 1 2 4 combination I am getting. That means to get this combination, what should be my S and R value? Okay, that means to get this state value, what should be my input? Qn is 0 and Qn plus 1 is 0. So it comes here and here. These two rows indicate Qn and Qn plus 1 is 0. Okay, so for this you can see S value always 0 and R value may be 0 or may be 1. Okay, that means irrespective of the value of R, if my S is 0, then I should get Qn as 0 and Qn plus 1 is 0. So we can write S is 0 and R may be 0, may be 1, so invalid condition. Likewise, if you want to find 0 1, 0 1 I can get from here. So only one condition 0 1. So for that my S should be 1, R should be 0. That means S should be 1, R should be 0. Clear? And to get 1 0 combination, 1 0 is available here, and to get 1 0 combination we will see my S should be 0 and R should be 1. So S should be 0 and R should be 1. And to get 1 1 condition, we can get it from here and we can get it from here. So these two rows indicate S is equal to 0 or 1 or R is equal to 0 is 0. And it clear that irrespective of the value of S, if my R is 0 always, I will get 1 and 1 in present and next state. So we can write invalid and 0. So this is nothing but the excitation table of SR flip-flop. Using this excitation table, we can convert one flip-flop to another flip-flop. In the next class, we will study about JK flip-flop. And JK flip-flop is actually takes the circuit of SR flip-flop. That means, so SR is my superset and JK is my subset. Okay, that means to develop a JK flip-flop, we have to use SR flip-flop. In SR flip-flop, due to some condition, we get invalid condition, and to overcome that, we have to go for JK flip-flop. Okay, thank you so much.